Okay. Today, qubit spline. Okay. Today. Section 6.4. Qubit. Splines. Yeah. I want to construct a spline function, the degree, qubit, degree free. Okay. Mathematics, to study mathematics, definition is the most important. Yeah, take a review about the definition of a spline function. Take a review. Okay. Yeah, review. Review. Yeah. What is a spline function? Okay. Given an interval AB. Yeah. Yeah. Right. This is A. This is B. B. Okay. Given an interval AB. Now, cut this interval into subintervals with points. Yeah. Cut. Yeah. Here. T0. T1. T2. And so on. This is Tn. Tn minus 1 and Tn minus 2. Okay. Now, over each subinterval. Okay. The first subinterval is a little bit tricky about this definition. The first subinterval is not A to T0, but A to T1. Yeah. So, yeah. A to T1, then open. Okay. Open at A, open at T1. Second, close at T1, open at T2. And then close at T2, open at T3, and so on. And the last subinterval is a Tn minus 1 to B. Okay. Yeah. Yeah. Tn minus 1 to B. The second last is Tn minus 2 to Tn minus 1. Okay. Yeah. And so on. Yeah. So now over each of these subinterval, okay, a spline function is a polynomial. Yeah, polynomial. Yeah, let me draw a polynomial. About different color. Okay. Yeah. Okay. Now A open. Okay. Yeah. This is a polynomial. Open. Yeah. From A to B, the spline function, the notation is say S. Okay. S. Yeah. S. Divide on A to B. Okay. A to B. From A to B, the whole function is S. Now, from A to T1, it is a polynomial. Let me denote this polynomial as 0. Okay, this is a polynomial. Okay, polynomial of degree k. Okay, at most k. I should say that. Okay, not exactly k. Yeah, at most k. Yeah. Okay, now T1 to T2 polynomial. Okay. Close at T1, then polynomial. This is a S1. Yeah, polynomial of degree at most k. At most k. Right. And so on. And so on. Here, this is a close at left left endpoint of the subinterval, then occur polynomial. This is a let me see. S m minus 2 x. Yeah. And then T m minus 1 to B. Okay. Yeah. And open. This is a S m minus 1 x. Yeah. So a spline function locally a polynomial. Okay. And also we require locally S is a polynomial. Right. And globally, we require this function is sufficiently smooth. Okay, we require this is a smooth k minus 1 derivative has k minus 1 order, and each derivative is continuous. Yeah, continuous on AP. This is a spline function. Okay, now today I want to construct cubic splines. Cubic spline, that means that degree k is number 3. Yeah, cubic spline popular. Popular in practice. Okay, commercial software. Can construct cubic spline for you. Yeah, cubic spline to approximate the unknown function f. Actually, f we don't know. Right now, cubic spline. Okay. Now I want to construct a spline function we have a notation. The set of all spline functions together, the notation is n k now 3. I want to construct. Now given a table. T locked. T0 suppose given T1 T2 then Tn given. Now the second row is about S cubic spline. I want S at T0 the value beta 0. This is a beta 1, beta 2, and beta n. It is not about the value of the unknown function f. No. Each cubic spline, it has values at the root. Now, I want what? I want S at T0 is beta 0. S at T1 is beta 1, and so on. S at Tn is beta n. Yeah, I want to construct such S, so that these conditions, these equations hold. Okay, because because S is cubic spline. So over each subinterval polynomial of degree 3. So I can write. Okay. Okay. Now S0, yeah, you need to remember the figure that I just erased. Okay. S0, it is a polynomial. Let me write this polynomial. A0 x3 B0 x squared C0 x and then D 0. Okay. What is x? X is in the first subinterval. Yeah, it is a polynomial. Then what are the coefficients? A0, B0, C0, D0 will be determined. Okay, will be determined. Yeah. Suppose we are given this. Okay. Yeah. This is a given. Okay. Given. Yeah. Given. So I want to determine A, B, C, D, so that the resulting cubic spline satisfy these conditions. Over the second subinterval is closed at T1, open at T2. Then S1, it is a polynomial A1, B1, 2, C1, D1. In general, X is in TK plus 1. K, it is a AK, X3, BK, X2, CK, XDK. Yeah, right. And so on. The last polynomial is Sn minus 1, An minus 1, X3, Bn minus 1, X squared, Cn minus 1, X, Dn minus 1. Yeah. When X is in the last subinterval. Now, let me count how many coefficients we have. Okay. For S0, we have A0, B0, C0, D0, 4 coefficients. For S1, also 4 coefficients. For SK, 4 coefficients. How many X? 0, 1 to n minus 1. So in total, how many coefficients? 4n coefficients. I want to determine these 4n coefficients so that the resulting S is cubic spline, and also through these given beta values. I want to do that. Okay. Okay. Now S is cubic spline. So okay, because since S is cubic spline, S is continuous. Derivative is continuous. Second derivative continuous. Are continuous. On the interval AB, right? Everywhere continuous. This is definition. Yeah. Q. Yeah. K is n. A spline function has K minus 1 order smoothness. Now, let me use these conditions to build for n unknowns, to build for n equations to determine these unknowns. Now, how about let me focus on the general SK. Okay, focus on the general SK. Okay. The general SK. Let me draw the curve. Yeah, this is defined on TK. TK plus 1. Okay, now here, this is a general SK. SK. Yeah. Let me try to find out the coefficients for SK. Okay. Right now, because we want spline function go through the beta values, so we have what? We have first. Okay. First, we have. Let me use. About let me erase here. Erase here. Just keep. So we have SK at XK is equal to what? Is equal to beta K, right? Yeah, I just focus on SK. I want to determine AK, BK, CK, DK. First, we have this. And then SK at X T. K plus 1 should be beta K plus 1. Do you agree? Okay. Now, what is K? K is 0. K can be 0. Okay. When K is 0, S0, T0 is beta 0. S0, T1, beta 1. 1, 2. K cannot be, because the maximum is Tn, so K cannot be n. So yeah, n minus 1. Okay. So here, how many equations? 2n. So many equations. Here, 2n equations. This is a 2n. 2n equations. 2n equations. Okay, now we also require, S when SK satisfy these equations, automatically S is continuous. Okay, now let me. Okay, derivative is continuous. Let me here. From the continuity of S prime, we can have some equations. Okay. Yeah. You agree? It is a derivative K at TK is equal to K minus 1 derivative at TK. Yeah. You agree? Yeah. This is a SK minus 1 X. Yeah. Derivative is continuous at TK. So yeah, this guy derivative at TK should be equal to derivative of SK at TK. What K is? K K cannot be 0 because I know here. K is 0, then S negative 1. We don't have S negative 1. We have S 0. Okay, so K is start from 1. 2. Let me see. K can be M minus 1. M minus 1. So how many equations here? N minus 1 equations. We have 4n coefficients to determine. Now, how many? Now, 3n minus 1 equations we have. Then, okay, now, here, second derivative is continuous. So, very similar. Sk second derivative at T1, the Tk should be equal to this, right? Yeah. Second derivative is continuous, should be equal. So this is a K from 1 to n minus 1. So this is the n minus 1 equations. So in total, 4n minus 2 equations. We have 4n coefficients to determine. Now we have 4n minus 2 equations. Yeah, from the spline definition. Yeah, spline definition. S derivative of S, second derivative, all continuous from A to B. And also, require S. Yeah, through the beta values. Yeah, so yeah, this is all. So actually, we have two freedoms. Two freedoms. Because we have 4n unknowns. But 4n minus 2 equations. So we have two freedoms. Yeah, two freedoms. For those two, we can arbitrarily assign values for those two. Okay, now let me solve these equations for the unknowns. To the end, let me introduce. Okay. Let me introduce. Okay. Yes. Introduce. Okay. S, the spline function, second derivative at T0 is C0. Okay. What is C0? Will be determined. Yeah. Spline function at T1 is C1. What is C1? Will be determined. Okay. And so on. Spline function at Tm minus 1, Cm minus 1. Spline function at Tn is Cn. Okay. Now, okay. C0, C1. Yeah, these numbers we don't know. These are unknown. Okay. I will determine unknowns. Okay. Okay. Now I will determine C. Okay. Okay. Focus on this guy. Then second derivative at Sk at Tk is equal to Ck. Yeah, Ck. Okay. K second derivative at k plus 1 is equal to ck plus 1. ck plus 1. K plus 1. Now, this is the starting point. Okay, starting point. Let me build a linear system about C. Okay, about the unknown C. Okay. Now, compare second derivative on ck. This is a ak x3 plus bk x2 plus ck x plus dk second derivative, take derivative. So it is a take derivative, second derivative, take derivative. So 6ak x plus 2bk, right? Second derivative. Now, plug this into AK, BK, I don't know. I plug this into these two equations. Then I can solve AK, BK in terms of CK plus 1. So the equation is, so the equation is this, okay? SK, second derivative, is CK unknown. But when I plug this into these two equations, I can solve for AK, BK. I can express AK, BK in terms of C. This is a HK. What is HK? HK is a TK plus 1 minus TK. And then TK plus 1 minus X. Plus CK, TK plus 1 minus TK, then X minus TK. So I express SK. I want to express SK in terms of CK plus 1. Yeah, this one. CK plus 1. We don't know yet. We don't know what they are. Okay, but yeah. Hey, now from here we cover SK. Take integral. Take integral. Now take integral twice, then I get SK X is CK 6 TK plus 1 minus TK. Yeah. And then TK plus 1 minus X3 plus CK plus 1. 6 TK plus 1 TK, and then X minus TK. What is TK? TK, we know TK. The lots are given. And then plus take integral. So C integration constant. Yeah, take integral. We have integration constant. X minus TK plus D TK plus 1 minus X. Yeah, take integral on this, then we get this. What is C and D? Yeah. Let me express C and D also in terms of CK plus 1. Then how to here, let me use this condition. Here. Yes. Plug in TK in X, then set the result to beta K. Plug in TK plus 1 in X, then set the result to beta K plus 1. Then we have C and D. Now, the final the result is CK. X is CK over 6 TK plus 1 minus TK. Then TK plus 1 minus X to the CK plus 1. 6 TK plus 1 minus TK. Times X minus TK to the actually here. Okay. Now let me. What is C? Yeah. How about let me? Yeah. I don't have sufficient space. C. What is C? C is beta K plus 1 over TK plus 1 minus TK minus CK plus 1. HK, yeah, because too tedious. Yeah, HK means this number. Yeah, this number HK. Over 6. Yeah, this is C. How about D? D is beta K over HK. HK means this minus CK. HK over 6. Yeah, TK. That's fine. So in this expression, what are unknown? Yeah. Unknown. We don't know. We don't know. Yeah, we don't know. Yeah, we don't know. Yeah. All other quantities we know. So I express SK in terms of CK plus 1. Right. Now we determine CK plus 1. Yeah. What else we haven't used yet? We have used this, okay, the continuity of SK when we said, yeah, these two equations they are equivalent to continuity. Yeah, when polynomials at the lots have same value, then the curve continuous. We have used this, and also we have used this. Yeah, we have used this because okay. When this is true, then the polynomials continuous at the lots. We have used this. What we haven't used is the middle one. Now I use the middle one to build linear systems for the unknown. What are unknown? Yeah, unknown. C0, C1, C2, unknown. Yeah. Cn, unknown. Unknown. Definition of C. Here. What? Definition of C. Yeah, I don't have enough space. Cubic spline second derivative at tk is ck. Yeah. Below if I see. What k? K is 0, 1, 2, and now let me use the middle equation to set up limit system. This equation. This equation. Take derivative on this. Plug in tk. Plug in tk, then we have hk minus 1, ck minus 1 plus 2 hk plus hk minus 1, and then ck. Oh, so tedious. hk ck plus 1. Yes. Yeah, here. Take derivative on this, plug in tk, then it's this. Now it's equal to sk minus 1. Replace k by k minus 1, then take derivative. Then plug in tk. Then we have no. Take derivative on this, then plug in tk. It's this. Yeah. Negative hk over k ck minus hk over 6 ck beta k hk plus beta hk over hk. Yeah. Take derivative on this, then plug in tk. Right, now sk minus 1. Yeah, replace all the k by k minus 1, then take derivative. Plug in tk. Right. So it's equal to hk ck minus 1 plus hk minus 1 ck minus beta k minus 1 hk minus 1 beta k tedious. Yeah. Here, this equation. What is k? K goes from 1 to n minus 1. So we have n minus 1 equations. Yeah. N minus 1 equations. Yeah. N minus 1 equations. How many unknowns? C0, C1, Cn unknowns. So we have 2 freedom. Okay. Which 2 you can know? N plus 1 unknowns. You can know arbitrarily pick 2 from them as free variables. Say usually pick C0. What C0 means? Second derivative of the spline at x0. Yeah. Cn, second derivative of the spline at Tn. Okay, Tn, not x0. Tn. Tn. Free. Okay. Yeah. Usually, yeah, choose C0. Cn as free. Okay, free. A common. Okay. We can arbitrarily set values for C0. Cn. A practice that we often use is set what? Set C0 to be 0, Cn to be n, to be 0, and the resulting cubic spline give a name, okay, because so common, give a name. Lateral cubic spline, the resulting, C0, Cn arbitrarily give values. You give other values, say 1 for C0, 2 for C1, Cn, then solve the linear system, we have a cubic spline. The cubic spline, we don't call it lateral cubic spline. Only when C0 is 0, Cn is 0, then the cubic spline is lateral cubic spline. Lateral cubic spline we often use. Right, now, how many unknowns? C0, C1 to Cn minus 1, Cn. N plus 1 unknowns. N minus 1 equations. Now, I give a value 0 for C0. Give 0 to this unknown. Then we have N minus 1 unknown, N minus 1 equations. Solve these linear equations for this, okay, for this. Then after we have the unknown C1 to Cn minus 1, then I know this. Yeah, plug in the value for the unknowns. Then I have this is a polynomial, the polynomial over the interval tk to tk plus 1. Tedious. Yeah, this is a cubic spline, okay, cubic spline. Use the properties of cubic spline. The properties of cubic spline is S is continuous, derivative continuous, second derivative continuous. Okay, recall at the beginning, beta 0, beta 1, beta n. We given values to these betas. So different beta values, we have different cubic spline. Okay. Yeah. So these are freedoms actually. They are free. Yeah. Free, arbitrary set. Okay. And also in the construction process, we load C0, Cn also free. So how many freedoms that we have? How many? 1 to n, then beta 0 plus 1. In total, n plus 3 freedoms. In other words, cubic spline. Yeah, this is a Sn to free, Sn free. The set of all cubic spline functions together. The set. This set is a space. Space means any two elements from the set, summation is still in the set. Any element from the set any number times the element still in the set, then the set is a space. This is a very mathematical. This is a space. What is the dimension of the space? Dimension of the space. Because we have n plus b freedoms. N plus b. We can arbitrarily assign values. So dimension is equal to n plus b. A natural question is, cubic spline, yes, popular. From the construction classes, you can take a look at my notes, very tedious. So tedious. Now, a question is, how to construct spline function degree 4? Oh, how to construct degree 4? How to construct a spline function of degree 5, and so on. Degree 3, so tedious. So actually, this process, construction process, cannot be used in the construction of a spline function of degree 4, degree 5, clearly, right? So we need to develop new approach. We want to easily construct a spline function of degree k, arbitrary k. Okay, how to do that again? That is what we will do. Okay, on Monday. Okay, on Monday. Yeah, I present one approach. And these are two details. Okay. I present approach to construct a spline function of degree k. K, what is k? Arbitrary. How to easily construct such a spline function? Next week. Okay, stop here. Yeah, take a look at my notes for the details. 2 tedious.